we have now talked about different types of inference rules, and about, in particular, about deduction and induction, and we've talked about Hume's problem of induction. One thing that I think kind of falls out of this discussion is that if we want to counter Hume's argument, we better pay close attention to the actual practices of induction that are performed. So we can't say, well, the actual practices are only justified if they cohere with the foundational principles. Rather, it's, as I argued in the coherentist perspective, is that it's the practices themselves that we need to look at, and we have to see which of them are justified in which situation. And therefore, I'll want to discuss one such broad practice in particular, which is the hypothetical deductive method. This is something that is widespread in the sciences, and it's not the only way how in the sciences we perform inferences. I've given you examples of simpler inductive inferences before, but the idea here is that, and you've already heard it in some of the answers of some of your fellow students, that in the hypothetical deductive method, we're combining deduction and induction. So we start by proposing or conjecturing a general hypothesis that is unproven. We just say, well, here's something we think might be true. And then we use deduction to derive certain consequences from that hypothesis. And then we test that hypothesis and either increase or decrease our confidence in the hypothesis based on the test of the implications. Let me discuss this in more detail. So here's a sort of more, here will be a typical sequence that you perform when you are performing a hypothetical deductive test. So you start by formulating a hypothesis, you're deducing observable consequences from the hypothesis, you test the hypothesis, and then you either infer that the hypothesis is false or that you can increase your confidence in the hypothesis depending on how the test came out. I'll discuss these 5 steps in more detail, and then in particular focus on these last 2 areas where you see what seems to be sort of different kinds of inferences, namely in 4, a form of falsification, and there we'll discuss Popper, and then in 5, the forms of confirmation. But let's start at the beginning. Sort of say it's not trivial. What is a hypothesis? Yeah, you're supposed to formulate a hypothesis. Well, does that mean you can formulate anything? No. Here are some requirements for what a hypothesis is, and certainly what a good hypothesis is, at least necessary requirements for a good hypothesis. So the first thing to note is that a hypothesis must be either true or false. That excludes a lot of statements that you can make. In particular, it excludes research questions. It's a huge difference between saying, oh, what are the consequences of this as the basis for your investigation? Or saying, the consequence of this particular experiment will be that the temperature rises by more than 20 degrees. So the question is not either true or false. It just doesn't have a truth value, while the latter one clearly has a truth value. It's either true or false. And therefore, you can then move on testing it. So that's the first requirement. The second requirement is that you have to watch out that you don't end up formulating a hypothesis that we would call as a tautology. Tautologies are claims that are necessarily true or false. So, for example, in English, a bachelor is often defined as an unmarried man. And then to claim that bachelors are unmarried is necessarily true. So if you have the definition of a bachelor and then you claim that bachelors are unmarried, there's nothing in the world that can make that sentence false. No, there's nothing that you observe in the world. So here we have a situation where we're just basically tickling out, or unpacking some of the ingredients of the definition, and therefore the claim is necessarily true or false, and therefore it's not particularly useful for any sort of hypothesis test. So we throw that out too. Can't be necessarily true or false. And then a third one is that a hypothesis either is supposed to have a certain amount of generality. So it's not supposed to say something about this particular thing, but rather about things of this type. Let's say work in a particular way. Or hypotheses can be about particulars, it can be about this particular, but then it should be something that is not directly observable. To say that this thing has some black surfaces under a particular light source is something that doesn't serve very well as a hypothesis, because all we do is to go observe it, and then we can say, then we describe the observation that we make, and that's it. So much for setting up a hypothesis and being mindful of what a good hypothesis is. The second step then is to say, okay, so now we have our hypothesis, and we now want to deduce some consequence of it that we can go and test. And here, the consequence, of course, should be directly observable, or it should be observable with the help of some instrument. And this might involve some operationalization, but in any case, we need to have a very clear. It's pointless to derive consequences that cannot then be observed, therefore cannot be tested. The deduction, of course, must be valid, and the consequence must be relevant for the hypothesis. This is a bit more complicated concept, because there are examples where you can derive consequences from a hypothesis that then the observation of which should not lead to a confirmation of the hypothesis. And I'll come back to that later on. Instead, let's do another little quiz. Namely, if we are only interested now, focus only on showing that a certain hypothesis is false, what kind of consequences do we need to derive here? So I'm asking you here's to consider the following hypothesis. If a card shows an even number on one face, then its opposite face is red. And now you want to show, or you at least want to test, whether to reject this hypothesis. Okay, so let's think about the hypothesis one more time. It's a conditional statement. It says, if the number is even, then it will be red. And then in order to prove it to be false, you have to figure out when this statement is false. And the only way that it is false is when it is even, but on the other side, it's not red. Therefore, you need to turn over those cards that show an even number, and those cards that don't show red on the other side. As you said, if it shows red, then whatever is on the other side is fine. But if it doesn't show red, then you need to make sure that it doesn't have an even number on it, because that would show that this hypothesis is false. Therefore, you needed to flip over B and D. This was to show that often it's quite tricky to figure out what the right consequences are you need to deduce from your hypothesis in the hypothetical deductive method in order to then argue that, for example, it is false or it cannot be false. Okay. So now we have performed our deduction, and now we're determining whether this consequence, this observable consequence, is true or not. And I will not discuss this here. This is something that we will discuss in lectures on measurement and experiments when we actually look at empirical practices. Instead, let's look at the last two steps. And here what you see is that we can either, in one step, if we observe the consequence to be false, then conclude that the hypothesis is false, or if we observe the consequence to be true, then increase our confidence in the hypothesis.